You've probably learned that a carbon atom bonded to 4 different groups is chiral. But what about a metal atom, bound not to 4, but to 6 or even up to 8 ligands? Even when several of those ligands are identical, the arrangement in 3D space can still be chiral. This chirality, called metal-centered chirality, or chirality-at-metal, is surprisingly common. And yet, it is routinely overlooked, even in published crystal structures. In this video, we present a new visual tool, a set of decision trees, that makes identifying metal-centered chirality fast, straightforward, and accessible to any chemist. In organic chemistry, the rule is simple. 4 different substituents around a carbon means a chiral center. But metal complexes frequently have coordination number 6. In the case of F-block elements, up to 8 or 9. Here's the surprising part, even a complex like this, with 3 pairs of identical monodentate ligands, can be chiral. Why? Because the way those ligands are arranged in 3D space around the metal atom can produce a non-superimposable mirror image. This is graph-level chirality. It depends on connectivity and spatial arrangement, not on having 4 different groups. The consequence is that chemists often synthesize chiral-at-metal complexes without ever realizing it. Standard analysis focuses on bond lengths and angles. It tends to miss this subtler stereochemical property. Metal-centered chirality is not just an academic curiosity. It directly influences chiroptical properties, for example, circularly polarized luminescence. Lanthanide complexes that are chiral-at-metal can emit left or right circularly polarized light with remarkable efficiency. This makes them valuable for organic light-emitting diodes in next-generation displays. They are also employed in advanced biosensing, operating through a precise sequence. First, molecular recognition and target binding based on their handedness. Then, sensitization via ultraviolet irradiation. And finally, the emission of circularly polarized luminescence. Chiral lanthanide complexes are even being developed as authentication inks for security applications. In all these cases, knowing whether your complex is chiral, and which enantiomer you have, is essential. That is precisely where the decision trees in this work become a powerful tool. Our decision trees are flowcharts of binary yes-no questions. You start at the top, the root, answer a question about your complex, and follow the appropriate branch. Each branch leads to either another question, or a terminal leaf node. The leaf tells you the probability that your complex is chiral-at-metal. The key insight in this work is that only a few questions, based on ligand type and count, are needed to classify most complexes. To see how these questions work, let's look at how we categorize and label ligands. We represent any complex using generic formulas, sorting the ligands systematically by their frequency. For monodentate ligands, those that attach at a single point, we use lowercase letters, A, B, C, and D. The rule is simple. The ligand with the highest count is always labeled A, the next highest is B, and so forth. For instance, a square planar complex with 2 identical ligands and 2 different ones is categorized as Ma2BC. In our visual example, all A ligands are colored red, the B ligand is blue, and the C ligand is yellow. If all 4 monodentate ligands are distinct, the formula is simply MABCD, with D in green. For bidentate ligands, which attach at 2 points, we use pairs of uppercase letters. If the ligand is symmetric, meaning its 2 coordinating atoms are topologically equivalent, we label it AA, BB, CC, and so on. If the bidentate ligand is non-symmetric, having 2 topologically different binding ends, we label it AB, CD, or EF. The exact same sorting rule for monodentate ligands applies here to bidentate ones. By defining these strict labeling rules, every specific chemical complex maps to a single, uniquely sorted generic formula. Let's start with coordination number 4, the tetrahedral geometry, which you already know from organic chemistry. The decision tree here has just 2 levels. First question: how many units of the most abundant monodentate ligand, labeled A, are present? If more than one, the complex is not chiral. This matches the rule you know: 2 identical substituents remove chirality. If A is 1 or 0, we ask a second question. Is there a symmetric bidentate ligand, type AA, in the coordination sphere? If yes, still not chiral. The 2 equivalent coordinating atoms of AA create a mirror relationship. Such is the case of chlorodiazarine, of chemical formula CHClN2. In our formalism, this molecule has the generic formula MABAA. Therefore, the molecule is not chiral. If the complex has no bidentate symmetric ligand, the complex is 100% chiral-at-metal. Formulas like MABCD, MABAB, MAB2, or MABCD all fall here. This is exactly what organic chemistry tells us: the coordinating positions must be non-equivalent for chirality. The decision tree simply formalizes this in a structured, scalable way. Now let's step up to coordination number 8, specifically, the square antiprismatic geometry, SAPR8. This is the most common geometry in lanthanide complexes, and the tree branches out significantly more. In fact, the flowchart-like structure shown is just an excerpt of the complete decision tree for the square antiprismatic geometry. But here is the key point: because every branch is binary, you always reach a leaf node in just a few steps. Let's consider this 8-coordinate dysprosium metal complex of square antiprismatic geometry. Its crystallographic structure was retrieved from the Cambridge Structural Database. This coordination complex has 4 bidentate ligands bound to the metal center. 3 of them are topologically symmetric beta-diketenates, which are labeled as AA. The remaining bidentate ligand is a bipyridine derivative. Its 2 coordinating nitrogen atoms are not topologically equivalent, so it is labeled as AB. Thus, the generic formula of this metal complex is MAA3AB. So, let's find in our decision tree the probability of a metal complex like this, having this generic formula and this coordination polyhedron, being chiral-at-metal. First question: is the number of A ligands 6 or fewer? Yes. We proceed left. Second: is the number of A ligands 4 or fewer? Yes. Third: is the number of B ligands fewer than 4? Yes. Next, is there any non-symmetric bidentate ligand of type AB? Yes. Now we proceed right with the following question: does the complex have exactly 1 unit of this AB type ligand? Yes. We arrive at a leaf. The leaf tells us 100% probability of the complex being chiral-at-metal. In fact, for SAPR8, for large clusters of generic formulae exist where coordination chirality is virtually intrinsic, with the probability of chirality-at-metal at or above 99%. But are these theoretical predictions supported by real data? We searched the Cambridge Structural Database and analyzed over 2,700 crystallographic structures of lanthanide compounds. This is the result: in more than 56% of unit cells, at least 1 chiral-at-metal complex was present. For octocoordinate complexes, the most abundant coordination number, the observed frequency of chirality was approximately 75%. For coordination number 9, about 60%. Most of these crystallize as racemates, both enantiomers in the same crystal, related by symmetry operations. But 114 structures were enantiopure, and remarkably, 68 of those were chiral-at-metal without any chiral ligands at all. To summarize, metal-centered chirality is a common, often overlooked stereochemical property of coordination complexes. It arises even when ligands are repeated, because spatial arrangement matters, not just composition. Its consequences are real, from circularly polarized luminescence to crystal packing and molecular recognition. The decision trees developed in this work provide a fast, binary rule-based tool to assess the likelihood of chirality-at-metal. They cover coordination numbers 4 through 9, and all major coordination polyhedra shapes with mono and bidentate ligands. You don't need a computer, just your complex's formula and geometry. A few yes-no questions, and you have a quantitative probability. But what if you want to take this a step further and fully automate the process? We have integrated these concepts into our complex build software. This program automatically maps out all possible stereoisomers of metal complexes, streamlining the construction of each structure. Beyond identifying all stereochemical arrangements, the software explicitly tells you if a stereoisomer is chiral-at-metal and automatically pairs up the enantiomers. Once selected, it builds your chosen enantiomer for you, and even allows you to easily invert the geometry if you ever need the opposite configuration. The software is completely free. We invite you to scan the first QR code on your screen right now to visit complexbuild.sparkle.pro.br and download the program. The complete set of decision trees is available in the supporting information of the paper. Scan the QR code on screen to access the article directly. We hope these tools help bring metal-centered chirality out of the shadows, and into the standard vocabulary of coordination chemistry. Thank you for watching.